Good morning, Professor. Today we will present our project title called Turtle Head Identification System. So I designed a system that uses image processing and machine learning to identify the turtle automatically. My pipeline integration is the three main content. First one, we use the Euro V8 segmentation for the head region detection. We use HOPT, is a histogram of oriented gradient for the filter extraction. And the last one is the cosine similarity for the comparing individuals. I will guide you step by step from raw data to evaluation.
Next is pre-processing is first I start by reading to CSV file, one file browsing box and one for annotation. Then I clear both file name by converting them to lowercase and removing space. After that, I merge the two datasets using the image name and key as key. This give me a combined table that contain each image, its bounding box, and its identity level.
For the ROI extraction, is the head cropping. We using the bounding box data. Each total heads was cropped from the full image to focus analysis only the region of interest. This removes background noise such as water, sand, or other body parts. This step ensures that our later algorithm, both YOLO and HOG, process only relevant information.
After cropping, I pre-process all image to make them consistent. Each image is converted to grayscale, denoised using Gaussian blur, then enhanced by histogram equalization to improve contrast, and finally resize to a standard size of 224 by 224 pixels. The preprocessed image are saved into a folder called dataset total preprocessed. Next is uh, we apply data augmentation to increase the dataset size and diversity. Each image is slightly, slightly modified 3 times using random transformation, such as horizontal and vertical flip rotation, brightness and contrast change, and small shift or scaling. This helps the model learn to recognize turtle head under different orientation and writing condition. The augmented image are saved in the folder dataset total preprocessing augmentation. Yeah.
For the registration, the reference photo of the same turtle might be taken from the slightly rotated angles. To standardize them, I implement rotation registration using the image moment. This method computes the main orientation of the turtle head and rotate into the eyes aligned horizontally. This small correction significantly stabilizes the gradient-based feature because Hawk is sensitive to orientation. Unaligned head could lead to mismatch gradients.
For the segmentation part of our turtle head detection project, we use YOLO V8. This model training our dataset for 50 airports using a branch size of 8 and image size 640. Unlike standard object detection, segmentation not only draw bounding boxes but also generate a precise pixel mark for each total height. This allows the model to understand the actual shape of the height, not just its position, which is important for accuracy feature extraction later. For the graph, this graph showing the training progress of the model. The first plot here is box loss, which measure how accuracy YOLO learned to locate total height with bounding boxes. As we can see, both the training and validation box loss strategy decrease, indicate that the model is learning to precise each height. The second plot is segmentation loss, which measure how accurately the model predicts the pixel level shape of the total height. The the segmentation loss also dropped sharply at the beginning and stabilized around f 40, showing that the model has learned consistent and detailed height boundaries. For the confusion metric, after training, YOLO generate a confusion metric to evaluate the model classification accuracy. Since our datasets had one main class, height, the metric help visualize how many predictions were correct versus incorrect. The strong diagonal pattern here indicate the most prediction match the correct level, confirm that the model has consistent total height. For the F1 curve, represent the balance between precision and recall across different confidence thresholds. The curve rises quickly and stay close to 1, which means our model maintain a strong balance. It rarely miss total height and also avoid false detection. A stable F1 curve near the top show that our segmentation model perform very reliability. Finally, we also implement Hawk feature extraction. The Hawk help visualize and describe how edge and gradient are distributed across the image, which is useful for shape-based recognition. For the result, the top two images show the original grayscale total height image, and the bottom two show their Hawk visualization. The bright line and arrow pattern represent strong gradient direction, capturing the shell and height structure. This feature can later be used for traditional machine learning methods like SVM.
To evaluate the recognition performance, I have created a set of positives of the same total and generate a negative pair, which is the different totals, and compare it with and compute its similarity. And this is the result. The AUC score of 0.586 and the main positive similarity as 0.63, and for the negative similarity is 0.613. The ROC curves show that the limited separation, meaning the overlapping between the positive and negative pairs, this is expected since the Hawk feature are handcraft and cannot be captured the subtle colored or scale differences. And while the Hawk-based system demonstrated the pipeline functionality, it also revealed its limitations. The main challenge are the lower interclass variance. The turtle look very similar, and the small lighting change can affect the gradients. Also, we have a limited data. The small data set reduces generalizations. A Hawk is also really sensitive, which will cause a performance drop if aligned slightly off. To address this in the future version, we could use a deep feature extraction from pre-trained models, such as a ResNet 50, VGG16. And for the conclusion, the data set pre-processing and augmentation, YOLO segmentation, and Hawk feature extraction with a comparison using cosine similarity and quantitative evaluation with AUC. For the future work, we could improve by focusing on integrating a deep learning feature extraction for more discriminative embedding and expanding the dataset with more turtle and the angle, and using the real-time YOLO interface to automate the cropping, and building a web-based interface for wildlife researcher to upload a photo and get the ID predictions. To summarize and conclude this project, the turtle head identification system demonstrate how classical computer visions and modern deep learning can work together to solve a real-world problem. Thank you for your attention.